Hi everyone. Nice to meet you. The purpose of this webinar is to explore the RC shell design of midasGen. midasGen provides automatic design of mesh shell element and already verified by many users. The program also supports section checking when relevant data is specified. We can learn the theory of shell design and know the calculation of shell design through this webinar. The table of contents is as follows. First, a brief introduction and theory of the shell design. Next, we will learn about the method of shell flexural design and shell shear design. Additionally, we will look at optimal flexural design. The program provides the optimal design and derives the optimal sandwich thickness. Last one is verification with sample modeling. In the case of meshed slabs, only out-of-plane moments and shear forces are supported. So we cannot achieve the desired design results when resisting in plane axial forces and moments due to lateral earth pressure, such as underground slabs. And the meshed wall design is also supporting only moment, axial force and shear of in plane. However, it does not consider out-of-plane. So we can't get the design result of 2D member that must consider a member force of out-of-plane and in plane together, like a dome structure. Since shell design supports a design that take into account all the components of internal force resultants, the design for plate elements that have not been designed due to limitations of slab and wall design is possible by shell design. With shell design of midasGen, a design for various shapes and loads is possible. You can successfully proceed with the project by designing 2D elements under any shape or load condition, such as irregular structures or structures for special purposes by midasGen.
I'm going to introduce the theory of shell design, that is sandwich panel theory. The program designs shells as per sandwich panel theory. One of the practical approaches is the report by Brondum-Nielsen. This work deals with the shell element as if it were a sandwich element composed of 3 layers. The outer 2 layers are not only responsible for resisting bending moments and axial forces. Inner layer also resists shear forces as shown on the right figure. In addition, to mathematically optimize the amount of rebar, the theory of Thomas and Marty was introduced, and an optimal design function was added in program. Let's look at the shell flexural design first. This chart is procedure of the shell flexural design. Design is carried out by distinguishing whether cracked and non-cracked sections occur due to design member forces. The crack judgment formula as follows: phi value. When the phi value is less than or equal to 0, it is judged as an uncracked section. If it is greater than 0, it is judged as a cracked section. In the case of the cracked section, proceed in the order of step 3 to step 8. If it is identified as the uncracked section, from step 2 to step 8 is immediately applied. The crack judgment formula, phi, is shown in this equation. As I mentioned, if phi is greater than 0, it is regarded as a cracked section, and if phi is less than 0, it is considered an uncracked section. The stress, sigma 1 and sigma 2 of the shell elements in midasGen can be checked in the plate stress, L, tab of plate stress table. In the table, sigma max value means sigma 1, and sigma min value is equal to sigma 2 value. Let's look at the procedure of shell design with uncracked section. As you know, when phi value is less than 0, it follows the uncracked section procedure like this chart. To secure the safety, the design principal stress, sigma 1 and sigma 2, must have a value less than the compressive strength, sigma Cn. However, if sigma 1 or sigma 2 is less than 0, you should use equation 1 for calculating concrete compressive strength, sigma Cn. And if sigma 1 and sigma 2 are greater than or equal to 0, you should use equation 2 in order to calculate concrete compressive strength, sigma Cn. Lastly, minimum absolute value of the sigma 1 and 2 should be lower than sigma Cn in the shell design of the uncracked section. And we will look at the procedure of shell design with cracked section. As you know, when phi value is more than 0, it follows the cracked section procedure like this chart. At first, use the plate forces. It is needed to membrane forces decomposition of externally applied loads. After calculating membrane forces, in step 2, you can calculate normal design forces N rebar X and N rebar Y for rebar and N con for concrete. According to the ratio of NEDX and NEDY to NEDXY from membrane forces, it is classified into cases 1 to 4. In step 3, you can check the concrete strength ratio and then you can calculate the required rebars for flexural design or check the used rebars for flexural checking in step 4.
Let's take a closer look at the procedure for cracked sections. Step 1. Membrane forces decomposition of externally applied loads. In a cracked section, a sandwich model is applied, and the outer layer resists bending and axial force as I explained. The axial force acting on the outer layer is given in these equations. J layer and opposite K layer. The value of axial forces for x, y, z directions and moment forces for x, y, z directions can be also checked in a plate force table in the plate force tab. Step 2. Calculate normal design force. The normal design force calculation formula should be applied separately in 4 cases. According to the ratio of NEDX and NEDY to NEDXY, it is classified into cases 1 to 4. The tensile and compressive normal design forces for each case are according to this figure. For example, if the values of NEDX and NEDY to NEDXY are greater than -1, then it is applied to the case 1. In this case, the values of N rebar X, N rebar Y, and N con are calculated by using the case 1 formula. In this figure, you can see the relevant design formula for each combination of membrane forces. Step 3. Check the concrete strength ratio. In the case of the crack section, the concrete in the compression section and the reinforcing bar strength in the tension section must be less than the design stress value to secure the member's safety. For the normal design force of concrete, N con is calculated in the step 2. And the strength review is performed according to equation 2.1, or equation 2.2 in this case is conditions and rho, minimum value. Look at the table of NU for the strength reduction factor for the cracked concrete. In Eurocode 2, NU value is different from concrete each compressive strength value. And in the case of Italy code, NU value is calculated by a slightly different formula. Not only Eurocode but also Italian code supports shell design in Gen. Step 4. Check the required rebar. The safety of reinforcement bar are also needed to check. From case 1 to case 3 in the step 2, a rebar is needed to reinforce in the layer where the tensile force is applied. The required amount of rebar, AS requirement, and reinforcement ratio, rho S requirement, is determined using the normal design force, which is calculated in the step 2. In program, the amount of rebar, AS requirement, and the reinforcement ratio, rho S requirement, are calculated per unit width. So, FT is calculated as dividing N rebar into CK, which is the depth of layer with compression. If the shell has reinforcement information using user input for flexural checking, the amount of rebar, AS, use of the shell can be calculated instead of A, S. Requirement. Let's look at the optimal design for shell flexural design applied in program. Optimal design means a design that optimizes the amount of rebar required by determining the thickness of the sandwich panel to the size of the membrane force, and secures the safety of concrete. In general, designing the shell proceeds with the assumption that the thickness of the sandwich panel, top layer and bottom layer, is from 0.2 hours to 0.3 hours, where h is the thickness of the shell elements. However, if it is assumed that it is thicker than the membrane force, the distance between the layer centers is shortened, and the required amount of rebar increases. On the other hand, if it is assumed to be thin, it may not secure safety, because the allowable value cannot be satisfied when examining the stress of the concrete. The optimal design functions in the program allow the users to search and determine the outer's thickness of the sandwich panel in order to secure the safety concrete. Optimal design will be explained in more detail. Step 1 is for calculating resultant moment, MA. The resulting moment due to the design member force is calculated by following equation 3.1. The resultant moment is an initial value for calculating K0, which is the thickness of the minimum compression layer in step 2. In the step 2, the Ck0, which is the first estimation of Ck from the resultant moment, is calculated according to the following equation 3.2. Step 3 is for calculating of membrane force in compression layer. By Ck, or Ck0, the interlayer distance from the central axis is changed. Membrane force for the changed value is calculated by transforming into equation 3.3. Step 4 is for calculating of concrete normal design force in compression layer. The concrete normal design force in the compression layer can be obtained from the equations in case 1 to 4 table of step 2. Step 5 is for calculating of second estimation of Ck. The second estimation of Ck is calculated by the following equation 3.4. In step 6, from step 3 to 5 is repeated. If the Ck of n step and the n+1 step is matched, the above processing is ended, and the last n+1 Ck is determined as the thickness value of the final compression layer. The subsequent design process follows design procedure of shell with crack section, which is explained before. Next is a shell shear design. Shear resistance of the section, VRD, should be greater than the design shear force for the section, VED. To satisfy limit state of shear resistance, the following condition should be met. VED is equal or less than VRD. Take a look at the VRD, the shear resistance. The shear resistance of shell elements is being reviewed only for the shear resistance of concrete. So it is applied that VRD is equal to VRDC. For calculating the design shear resistance of concrete, larger value of the following two equations, equation 4.1 and equation 4.2, are adopted. VRD1C and VRD2C are respectively the following formula, equation 4.1 and equation 4.2, where ASL is the area of the tensile reinforcement, which extends LBD plus D beyond the section considered. For beam section, program considers ASL as the area of the tensile reinforcement provided. For column sections, the ASL is used as the half of the area of the longitudinal reinforcement. And take a look at the VED, the design shear force. The design shear force of the shell element, VED, is considered the result of the design shear force of the two axes. So it is applied that VED is equal to VED0. The sum of shear forces can be calculated by using the equation 4.3, SRSS combinations. Through a sample example, we will learn about and verify the shell design function output from the program. The sample model for calculation verification is a cantilever structure, and the thickness and shape dimensions are shown this picture. 6 meters by 6 meters, thickness is 0.3 meters. As for the load input, the nodal load for applying the axial load, 10 kilonewtons to the plate, and the pressure load, 3 kilonewtons per square meters for bending were input. The target shell element is number 3 for verification. The concrete compressive strength is 25 megapascals, and rebar is 400 megapascals. We use design codes as per Eurocode 2. At first, the design comparison was performed on the bending design of the top layer of the shell. Step 1 is to define subdomain as a shell element. For shell design, the model must be modeled as a meshed plate for shell design, and a member type must be defined as a shell. With AutoMesh planar area, the one can easily create meshed plate elements. And the meshed plate should be set as the shell in the member type by using the define subdomain function. Here, users can set the basic rebar arrangement and rebar direction for shell design. With checking the base rebar for slab mat shell, we can define the basic shell rebar arrangement. Step 2 is to define the layer of rebar and sandwich thickness for flexural checking. In the shell design, there are 2 functions. Shell flexural design, which presents the amount of rebar to satisfy the resistance ratio less than 1.0, and shell flexural checking, which evaluates the resistance ratio for the input amount of the rebar. For shell flexural design, a reinforcement standard is required to calculate the reinforcement arrangement information for the calculated reinforcement amount. On the other hand, for shell flexural checking, you need to input the rebar arrangement, and you can enter it in the dialog box. And define sandwich thick and optimal design. Shell design uses the sandwich model as I mentioned. In Gen sandwich model, the thickness of the outer layer is applied as a default value of 20% of the total thickness, and the user can directly input the thickness ratio. In addition, it provides a function to calculate the thickness of the outer layer for optimal design by checking the consider iteration for optimal design. Step 3. Run shell design and checking. It can display the result of the shell flexural design and checking in the mesh design menu. You can check the flexural design results for shell elements in Contour for display and produce the detailed flexural design results of shell elements in a text format. Also check the resulting bending moments and the design results of reinforcement. In shell flexural design checking dialog box, you can see the following's contents. When you check the rebar option, you can display 9 cases of flexural design results. First one is member axial forces. Axial force for member displays the axial forces per unit width of top-bottom layers of the sandwich model. Membrane shear force displays in plane shear forces per unit width of top-bottom layers of the sandwich model. Rebar stress displays tensile stresses of reinforcement. AS requirement and rho requirement display the area of the required reinforcement and required reinforcement ratio. Last is rebar arrangement. You can see the bar spacing in Contour, which is placed in plate elements using standard bar sizes defined in the slab wall shell rebars for checking menu. In concrete option, you can display principal compressive stress of concrete as well. MIDASGen produces the design result table and detail flexural design results of shell elements in the text format. Let's verify the design result table and Contour for display of the target element number 3 member. The design result table faithfully lists the procedure of flexural design as I mentioned. First, check if it is cracked or not. Then, calculate membrane force. You can check the membrane force value as a graphic contour. Step 3. necessary reinforcement and concrete stress. Element 3 is involved in a case 1 according to the value of membrane forces. Step 4. Check the concrete strength and required rebar. And in Step 5, it finally evaluates whether the flexural design secures safety for rebar and concrete. All these steps can be checked with contour for display. Now let's look at the shell shear checking in Gen. In the same way as the flexural design, it can display the result of shell shear in the Mesh Design menu. In the shell shear checking dialog box, you can see 3 cases of the shear checking results. First one is VED0. It displays the shear forces per unit width of the plate element. And it shows the shear resistance as per unit width and resistance ratio, the ratio of the design shear force to the shear resistance. It also produces the design result table and detail shear checking results of shell elements in the text format. Let's verify the shear result table and contour for display of the target element number 3 member. The design result table faithfully lists the procedure of shear design as I mentioned. First, calculate design shear forces of the inner layer. VED is considered the result of the design shear force of the 2 axes. So VED0 is the value of the SRSS combinations of VEDX and VEDY. Step 2 is calculating design shear resistance. As explained above, the formulas of VRD1C and VRD2C are calculated, and the larger of the two becomes the final VRD value. Finally, we calculate the resistance ratio. All these steps can be also checked with contour for display. This concludes our webinar on the shell design. Even though it was short, I was happy to give you an overview of the shell design and introduce the shell design in MIDASGen program. We look forward to seeing you at our next webinar. Thank you.